In this video, I want to talk about hypothesis testing. And we've done a lot of kind of nitty-gritty stuff with hypothesis testing, and if you've forgotten some of it, I would urge you to go back and watch earlier videos on kind of the specific tests. But I just wanted to do kind of a broad overall picture here and talk about things that you would want to look for. So in each one of these, let me just explain my table, like how do you know which test to use? What's the state portion? What are the plan? What are the conditions? And the do. What test is it? What do you return? And just overall, I want to talk about those three parts of your conclusion. So in a t-test, what do you look for a t-test? Well, obviously, you look for a sample mean. Okay, that is true of these two as well. In a t-test, you look for a deviation, okay, a sample deviation. I'm going to write that. And you look, in this case, for one sample size. Okay, so that's a 1N. That's what that stands for. And here, you end up with two of them, right? You have two samples, in which case you should have two deviations and two sample means. Now, the matched pair is the hardest one to kind of pick out of this, because oftentimes you are given two sets of data and you condense it down to one. So we look for, really, is there an important reason to pair data together? Okay, and that's something that's sometimes hard to pick out. It's obvious when it's like a before and after situation. You say, well, it's, the person before the diet and after the diet. That's easy. Other times it's harder. Let's say you're comparing heights of fathers and sons. That's important to pair a father and son together. You can't compare one boy to a different father. So you have to look for, is it important that I pair this data together and then boil it down to a difference? And that's the other thing. You end up with just one mean and one deviation, and those are for the difference. I'm going to write this. I'm sorry, it's getting a little messy. The difference. So this two sample t, this is the only time you have two x bars and two sample deviations. Okay? Proportions. What do we look for? Well, we look for a proportion, or we look for a, x out of n. Like, oh, we had 15 out of 500, something like that. In two, we have two proportions. We have basically two samples, two n's. Okay? In a chi-square test, the first thing that you could look for both chi-squares is more than two categories. Okay? More than two categories. The minute you start talking about putting things in 3 or 4 or 5, it's no longer a proportion test. It's on to chi-square. That's for both. For goodness of fit, basically you look for one set of expected value, or one set of observed values. And in an independence test, you look for a table of observed values. Basically, you've broken into categories in two directions, right? That you have, you're saying, well, I broke it down by not only their class in school, freshman, sophomore, junior, senior, but then I also broke it down by their income level or something like that. You've broken into categories in two directions and almost made a table of it. And linear regression is probably the easiest to spot, because obviously you're talking about the slope, right? You're looking for a pretty specific type of test here. All right, so now the state. In every single state, this is where you do your null and your alternative, okay? And I'm going to write down kind of the nulls. So we have a mu equals blank, the population mean, and we have a number. And remember, you have to define your mu. You say mu is the population mean and put it in context. Okay? Now, with two samples, the null is mu1 equals mu2. And I'm not going to write the alternative. Obviously, it's a different inequality. It's greater than, less than, not equal to. Same thing is true here. It would be, mu is not equal to, greater than, less than. That same number. Use the same number in both spots. Here you can use subscripts. You could say like the average 20-year-old is equal to the average 30-year-old. You can use subscripts to define your variables if there are two samples. So going on to the matched pair, remember that the matched pair, the null, because we've condensed it down to one list, is the mu is equal to 0, that there was no difference. And again, your alternative would just be, greater than, less than, not equal to. A one proportion test. So the null is that P is equal to blank, and for a two proportion, P1 equals P2. And again, same rules apply here as the T in terms of, first of all, make sure you're using a parameter to state your null and alternative. It should be the same values in both, same numbers, right? And if you only had one sample, define that parameter. What does P stand for? It's a population proportion. And if you have two, you can use subscripts. The proportion of men equals the proportion of women, or something like that. Okay, you can use the subscript. So again, make sure you're writing this correctly. Make sure you are using parameters. Make sure you're keeping the numbers the same if it was a one sample. Okay. Now the goodness of fit. This is remember we have the observed is equal to the expected. And we have this, kind of a fill in the blank piece like that. It's the observed distribution of scores is equal to the expected distribution of scores. The observed distribution of ice cream cone types is equal to the expected distribution of ice cream cone. So you really observed distribution equals expected. Now the chi-square test for independence, the null, oh, I'm sorry, I didn't write a null here. The null is really that the two variables are independent. Okay, so that, you put some context to that, but that's the null. That your class is independent of your gender. Your GPA is independent of your attendance. Something like that. Okay, and for linear regression, the null, remember this is where we have that beta. The slope is 0. And again, we have to define that. The beta is the population slope between, X and Y. All right. Now, during the plan portion, everything needs to be a simple random sample. We want good data for everything. Okay? For the t-test, and for all of the other tests, we have that 1/10. Sample size is 1/10 the population size. Okay? Remember here, we want samples that are 30 or larger for these three. For proportion, we use that NP is bigger than 10, N times 1 minus P is bigger than 10. Okay? For chi-square goodness of fit, we use that expected count is bigger than or equal to 5 for both of these. Remember, you should be writing those down. If it's a chi-square test, you should write down those expected counts. For goodness of fit, you might have to calculate them. For independence, remember, it would be put into a matrix and you could recopy it down. Okay. For the two samples, we need the samples to be independent. I'm going to add that here. Independent samples. And again, that goes for the two proportion test as well. It obviously doesn't go for chi-square because they are dependent on one another. The last one, kind of the different condition here for linear regression, you remember it's liner is the way we write it. And that stands for Is the data linear? Were they independent samples? Is the distribution of residuals normal? Is the standard deviation equal? And was there randomly collected data? Okay, so again, linear trend, independent samples, normal distribution of residuals, equal deviations throughout the linear approximating, and finally, was it random? It's at this portion in the plan where it's always also nice to name the test. To actually write down, these are the tests I'm using. To write t-test, two-sample. And I'm just going to make a note of that. It is nice at that point to name the test. Okay, the do portion of this is all done with the calculator. Tell what the test statistic is. So for t, of course, it's a t. So remember your degrees of freedom. Remember, you could do that as a subscript for those two. For a proportion test, it's a z. Here it's a chi-square, and remember again, degrees of freedom. And here it's a t, so remember degrees of freedom. Now remember here for these t statistics, the t is the degrees of freedom is sample size minus 1, and for linear regression it's sample size minus 2. Okay, so remember, report your test statistic, and if degrees of freedom are necessary, the only time it's not is the proportion test. And then give your p-value. Okay, so the do should have two pieces to it. Finally, the conclusion is 3 parts. Okay, for all of these, it's 3 parts. First part. Okay, first part. Say what you're doing with the null. Are you rejecting or failing to reject? Okay, tell what you're doing with your null hypothesis. That's number 1. Second piece, tell why in terms of the p-value. Why are you doing that? It's because the p-value is smaller than the significance level, so your p-value is less than 0.05, reject. Or are you failing to reject because the p-value is bigger than the tell why. And the third is, what does that mean in context of the problem? We have evidence that the mean is higher than it used to be, or that the two proportions aren't the same. Okay, so use that we have evidence, or say we don't have evidence. We have insufficient evidence. Okay. So again, you may want to look back at some of these kind of individually, but this was an overall idea of all the different types of hypothesis tests. Be very careful in your work. These are typically not that hard on the AP exam, but they do require some, being exact with your null and your alternative and the way you show your work. I wanted to add one final test on here that I didn't include, and that is the chi-square test for homogeneity. And let me just explain what that test is. It's very similar in its work to the chi-square independence test, and oftentimes these two have a link together, and that very often our information is given to us in like a two-way table, where we've got like things kind of categorized like in here, and then we have counts inside. And here's the difference. A chi-square test for independence gives us one sample where people are basically asked for 2 pieces of information. So maybe we sample 1,000 people, and each person we say, how old are you? And who are you going to vote for in the next election? That is 2 pieces of information, and we say, okay, break them into age brackets, candidate A, candidate B. That's the chi-square test for independence. The null would be that candidate preference is independent of age group and so on. The chi-square test for homogeneity rather takes samples and then creates a distribution out of these multiple samples. So
using that same kind of logic, here's how a homogeneity test would be worded. I wanted to sample 200 people that were under the age of 35, 200 people that were between 36 and 50, 200 people that were between. So basically, I'm almost like stratifying my sample. Certainly, it's not important that they all be the same, but I'm pre-creating this age group, and then I ask within each age group, okay, what candidate are you going to vote for? So multiple independence is one sample where we break people into categories in a couple ways. Test for homogeneity is multiple samples, okay, but it does look the same. Another way, maybe an easier way to think of homogeneity is sometimes we do this like think about the AP exam. In 2010, here were the counts in class of 1s, 2s, 3s, 4s, and 5s. In 2021, here were the counts of students that got 1s, 2s, 3s, 4s, and 5s. Same categories, right? What AP score you got, but two samples, and you're comparing those two samples against each other on multiple categories. Okay, so that's what we're kind of looking for are, two samples. I guess we could have more. I'm going to put or more plus, and then multiple categories. That's what we're looking for. The null basically is that the two samples or two populations rather, are distributed the same. And of course, if you had more than two samples, so you'd say however many samples you took, those populations are distributed the same. So with my AP example, you'd say, well, the null is that the 2010 and 2021 distribution of scores would be the same. Okay. The plan for the chi-square test for homogeneity is going to be really similar to the independence one in terms of, our need for the expected counts to be greater than 5, for the sample size to be less or equal to 1/10 the population. The one thing we can add in here is that because we had multiple samples, we have independent samples again. That wasn't true on the chi-square test for independence because we took one sample and then we just broke them into multiple categories. The test statistic and how we type this in is literally the same. It's going to appear exactly the same. We're going to put it into our matrix and run the test, and just don't forget to go back and rewrite your expected matrix down. And your conclusion, you'll reject or fail to reject in the p-value, and then you'll add the context. You'll say we have evidence. If the p-value is low, you'll say we have evidence that the two samples are not distributed the same. So in my example, we'd say, well, we have evidence that the 2010 and 2021 distribution of AP scores are not the same. Something like that. And if the p-value is high, we say we don't have enough evidence to say that there's a difference between the breakdown in 2010 and 2021.